Reuven, are you ready? Where are you? Here,
Yeah.
I can see you. Okay, so our next speaker is Reuven Balkin. Reuven is our first year postdoctoral fellow. He is at the Technion, he's a physicist, and he's in the lab of another Azrieli fellow, Yotam Sorek. So Reuven will speak to us about looking for new particles using stars. Reuven, the floor is yours.
Thank you for the introduction. So you can see my slides, right? Okay, so today I'm going to talk with you a bit about my work, looking and hopefully tell you how we can look for new particles using stars. So I think that people are curious by nature, and a good example of this is children. So for example, my kid would have a glass of water, and he would tell me, actually, he already knows. He would tell me, "Dad, do you know that water is made of molecules?" Say, okay, that's very interesting. And then he might pause for a second and ask me, but what are molecules made of? And I will tell him, that's a great question. It's made out of atoms. So for example, a water molecule has an oxygen atom in it. Then he would pause for another second and ask me, what are atoms made of? And I will tell him, well, they have a structure, and inside of the atom, there is actually a nucleus that is much, much smaller than the whole atom, actually 4 orders of magnitude smaller. And then again, he would ask, but what is the nucleus made of? And I will tell him it's made out of neutrons and protons that are another order of magnitude smaller than the nucleus itself. And then he would ask me again, what are nuclei made of? And I will tell him it's made out of up and down quarks, which already might sound like science fiction. And the next question would be, but what are those made of? And at this point, I have to say, okay, we actually don't know. We have some upper bound on these size, but we don't really know if the quarks themselves have any other, if there's any substructure there. And Feynman said it nicely. He said, there's plenty of room at the bottom. So these kind of fundamental questions are the things that interest me as a physicist. And to convince you that it's interesting and or important, let me just say, so to the question, why is it interesting or important? The first thing I want to say is just because, but that's arguably subjective. So to be more pragmatic, some people find it interesting because particle physics is very closely related to cosmology, which is the history of our universe. And also, practically speaking, understanding the rules of nature oftentimes leads to new advances in technology. So a great example of this is Einstein when he wrote down the general theory of relativity in the beginning of the 20th century. He had no idea that roughly 100 years later, it would be used in GPS systems. So that's a great example of how we don't really know, and we have to first learn the rules and then see how to use them. So in this talk, I'm going to discuss 3 main things. The first thing would be what we do know as particle physicists. What do we know about nature at these tiny scales? The next logical step would be to tell you what we don't know, or what we don't understand, what puzzles us, what keeps us busy. And the last thing is, where do I fit in? What kind of, I'll take one example, one question that I'm interested in, and how my research tries to answer it or find evidence for the solutions to these problems. So what we do know is roughly summarized literally here on a cup, and it's called the standard model of particle physics. So it's written schematically here on this cup. It contains a lot of information. And to tell you a bit of what it is, so firstly, it's a quantum field theory, which means that it combines the principles of quantum mechanics and special relativity, 2 theories that were developed in the beginning of the 20th century. It contains the information about the different particles and their interactions. And it depends on some unknown constants, which we must measure in the lab in order to be able to use the standard model. So for example, the mass of the electron, how heavy the electron is not a prediction of this model, but rather we have to first measure it, then input it into the theory. And once we fix all of our parameters, all of our input, we can then use it to actually calculate other things and check our theory. So you can And that's the point, is that the standard model is eventually a tool that we use to calculate physical observables that we can later go and test in the lab. Okay. So usually when you talk about the standard model, this is a type of diagram that one often sees, and it's all the particles of the standard model, the particle content. I found a much cooler cartoon of it, and this to give you the idea of this particle zoo. And let me go over it quite quickly. So we can divide the standard model into a few different sectors. So the first is the quarks, and they come, there's the up and the down quark, and they come in 3 copies that are very similar, only increasingly heavier. Their masses are larger and larger. Their defining features are that they have 3 types of charges: electric, weak, and color charge. And because of this last charge, the color charge, you never actually find these guys free in nature. They're always stuck close by to each other, because there's a very strong force color that's associated with color that keeps them together. So for example, neutrons and protons, as I mentioned, are made out of quarks, and specifically up and down. The second type of particles are called leptons. Here we have the ones on the left, they carry electric charge and weak charges, and the electron is quite known, and you can actually find it in nature, in atoms. The second time on the right are neutrinos. They only carry weak charge, so it means that they interact very weakly with the standard model. That's why they look like little ghosts here. And the third type of particles are the bosons. So each charge that I mentioned is associated with an interaction, which is mediated by one of these bosons. So all of the bosons are associated with forces. So we have the photon, which is quite known, is associated with the electromagnetic interactions. We have the weak interactions by the Z and the W bosons. We have the color interactions, which I mentioned, which are mediated by the gluon. There's a special guy here called the Higgs, which made a lot of headlines when it was discovered 10 years ago. And you can also think of it as mediating something like a Higgs interaction. And the last piece of this puzzle is the graviton, which mediates gravity, which is also a very known force. Curiously enough, it's not actually contained in the standard model, and I would go back to it in a second. I will mention it in a second. So this was the standard model, very roughly. What else can I tell you? Like the main points about the standard model would be, it accurately describes all the different interactions, electromagnetic, weak, and strong. It's consistent with various and numerous experimental tests. And the crown jewel of it was to predict the existence of the Higgs, as I mentioned, which was discovered in 2012. So Nathan Seiberg said it better than me. The standard model gives us an accuracy of 10 decimal digits. This is an amazing success that has never been achieved before in science. So by many, the standard model is considered to be one of the most, if not the most successful physical theory in human history. So having said that, there are a lot of things that we don't know or that we are puzzled by in the standard model, and I will start going over them. One very obvious one is neutrinos. In the standard model, they are massless, but in fact, we measure them to have mass. We don't understand where is their mass coming from? Why is the Higgs so light? We don't understand the origin of the Higgs mass, and we have reasons to think it's heavier. Why are there 3 generations? What is the origin of the mass hierarchies between the different copies of the particles? There's another problem called the strong CP problem related to one of the properties of the neutron, specifically the electric dipole moment. It's very small. I'll go into more detail in the next slide. And there are various other problems: quantum gravity, dark matter, cosmological constants, flavor anomalies, antimatter. So there are plenty of things that we don't know, we are puzzled by, which we are trying to understand. The bottom line and the conclusion from this should be that the standard model is in fact not a complete theory, and it has to be extended. By extended, I mean there are more particles, there are new particles that we don't know, and there are new forces that we don't know. So to be more specific, let's talk about the strong CP problem, which motivates my research, part of my research. So as I mentioned, the neutron electric dipole moment, it's a property of the neutron. It's proportional to a parameter of the Standard Model. As I said, we have some parameters in the Standard Model which we have to measure in the lab, called the strong CP angle. Now, we went to the lab and we measured this property of the neutron, and we find that this parameter is very small, 10 to the minus 10. It's a very tiny number. Now, on its own, that might not be a problem, but we have a very similar parameter in the Standard Model called the weak angle, and we find this to be almost pi, same order as pi. And I keep using the words angle, so it should be understood that we expect this to be something like an angle order 1 times pi. That makes sense. So when I see these two numbers, it makes me wonder, why is this angle so small? Is this a coincidence, or is there something behind this? So how can something like this be solved? What does it mean to solve problem in theoretical particle physics? So one possibility was brought up by Pecci and Quinn in the 70s, and it's called the axion. It's a hypothetical particle, and once you add it to your theory, the value of the theta angle is actually not a constant, but a dynamical property of the theory. It means that you can imagine you have a ball rolling in this well, and it rolls down to the value at the bottom, and it eventually settles down there at the bottom. And the effective angle that you see is the position of this ball. So you see, if I set it after a while to be theta, the value of this theta angle is essentially, we have some mechanism to explain why is it so low, or why is it actually close to 0 or 0. So that's very, very broadly speaking how something like that can work as a solution to the problem. Now to the last part, how can stars teach us about particles, and specifically the axion? So we're looking at neutron stars. So now I'm going to show you a little plot. On the x-axis, we have radius in kilometers. On the y-axis, we have masses in solar masses. And when a star is formed, when matter is crushed by gravity, it doesn't just crash randomly. It's governed by the rules of general relativity. So if you solve the equations, Einstein's equations for general relativity, you'll find a curve that relates the mass and the radius of these bound object of these stars. So each point along this curve corresponds to a solution of the Einstein equations. So if we don't have an axion and we look at neutron stars, they would live somewhere on this curve. But once we add an axion, it would actually change the properties of neutrons, and it would cause this curve to look completely different. So again, the axion interacts with matter. Once we add it to our theory, it interacts with neutrons and protons. It can alter the microscopic properties of matter, making also stars look different, have different masses and different radii. Why is this interesting? Can we actually see it? And the answer is that the near future is very exciting if you're interested in neutron stars. And the reason is gravitational waves. I don't know if you heard about the recent discovery of gravitational waves. It was highly publicized. So you can actually see very massive objects as they swirl towards each other, emitting gravitational waves. And there's a very nice plot from one of the collaborations, the LIGO collaborations. They have a catalog of all the events they have seen, and this increased by an order of magnitude in the last couple of years, and it would keep increasing in the next couple of years. And we'll have sensitivity to smaller and smaller objects, including neutron stars, some of which have already been observed even by LIGO. So there's a lot of information that's going to come in the next decade or so related to neutron stars. So it's interesting to see whether we can actually learn from neutron stars, these massive, gigantic objects, about the microscopic world. Thanks.
I'm taking down your presentation. I understand that I could, so that we can see everyone. Okay. Any questions for Reuven? Reuven, Jonathan has a question. Can you see, Reuven, can you see everyone? Can you see people's hands up? Okay, go for it.
Please. Yeah, and I'm not taking questions from you.
Okay, Jonathan?
Yeah, Jonathan, go ahead, but you're
You're
muted.
on
Sorry,
mute.
I lost.
Yeah.
Sorry, I couldn't hear you. Okay, so I was a little bit lost. Maybe you can explain again. So you were talking about the CP angle, and
Yeah.
then you were talking several explanation. One of them was a dynamic way to find that actually it should be zero, but because it's dynamically set to zero, then I imagine there's some kind of interference that make it to be almost zero and not. And I wasn't sure what you mean there. And the second question is, I'm not sure how it relates to the second part where you're talking about the collapsing stars. How does that relate to the dynamic view?
Okay, so the first part of your question, I am not sure I understood it. So
what exactly?
Yeah.
So you said that CP should be zero, but it's dynamically set to zero. So the fact that it's not real zero means there's some kind of interference in the dynamics. If it was just pure dynamics, why it still doesn't explain why it's only close to zero and not zero.
Okay, so the idea is that theta as the parameter could have any value, but what we see in the lab is not just this value, but also the position of this ball, as I mentioned, which is actually a value, some background value of a field that's all around us. So the idea is that you have some dynamical reason why you end up at being very close to zero, so which is what we see in the lab. At this point, there we have an upper bound. We actually don't see anything, so we just have an upper bound coming from the resolution of the experiment. So we actually don't see anything, and that gives you a dynamical reason why you don't see anything is because you have some dynamic relaxation of this parameter in the universe. The second part, okay, I rushed a bit there. The idea is once you add a new component, in this example, a particle, the axion, it would, what does it mean to add the particle? You add the particle to your theory, and you also add the interactions it has with matter. You add new parameters which describe these interactions. Now you try to see what is the experimental implications once you add this parameter. How can we see it? Can we see it in a collider? Can we see it coming in from space? Can we see it coming from the sun? So there are various ways to look for new particles. And my particular kind of approach is to see how it can affect neutron stars. And the reason why it can affect neutron stars is because it interacts with neutrons and protons, it can change their properties. And once you change their microscopic properties, it will change the macroscopic properties of objects like neutron stars. So that was did that answer the second part?
That in this case, you won't have the problem that you have in the lab that you said that you don't see anything because of the thing.
Yes, it's a different observable. It comes from kind of a different angle. So, once you add something like a particle, there are various ways or various implications. So one thing is this neutron electric dipole moment, but you can have other, an axion can talk to photons. So there are very cool experiments that try to get something invisible to pass through like a huge shielding, and then you pop 2 photons out of the vacuum because the axion talks to the photons. So for example, there are other ways you can look for it. So once you add a particle, there are a lot of implications, and you need to you think about what's the best way to look for it, what's the practical way of looking for it. Some things are possible in a lab today. Sometimes you need to build a collider that costs 100 billion euros, depends. Thank you. Yes, Jan.
Hello. Thank you for the nice talk. So now it will be a simple question.
Okay.
So you have shown a plot of the mass of the neutron star as a function of its radius. And you have shown that when you add the axion, for a given mass, the radius is smaller.
Yes.
So you take a neutron star, okay, it has a given mass, given radius. Now you add your axion in your universe, and then the radius is smaller, like the star shrinks.
Right.
So how can you understand this?
Okay, before you answer, Reuven, I'll just indicate that you have 1 minute to answer.
Okay.
Thanks.
Okay. So, okay, that's a very good question. The answer would require me to go into a bit more details about what actually happens. And in this specific plot, what I showed you is like the most dramatic effect is that the axion can cause a phase transition and cause nuclear matter to have different properties than it does. So nuclear matter is the usual stuff we have in nucleus. That's how neutrons and protons arrange themselves. And when you add the axion, it can go through a phase transition, making them lighter. And when they go to a new phase, they also have, it means that you have a phase having a new ground state, okay? Like nuclear matter is the ground state of neutrons and protons. You have a new ground state, and that ground state has constant energy density. And when you have something like that forming bound objects from gravity, it would actually, their curve would actually tend to zero. As the radius shrinks, the mass would also shrink. But we can discuss it in more detail later. It's a bit more complicated to explain given the information I gave in the talk.
I hope that you will discuss it later, because most of us, I think, in the room don't have the tools to understand what you're talking about. Okay, thank you. Thanks, Jan, for your question. Thank you, Reuven, for your presentation and for your in-depth answers.